So we are now at module 2.1 and we'll go through classical optimization techniques in the case of single variable optimization with no constraint. And you would notice that we are starting for most of the course with classical optimization techniques. And near the end, we'll go into modern optimization techniques. Classical and modern here may not mean what you come to your mind typically. Here we are talking about classical is a stuff that started 17th century by Newton, went through 18th century, 19th century, and sometimes even into 20th century, as we'll see later. Modern techniques started fairly recently, 70s, 80s, and it's still continuing. New algorithms are being proposed all the time. And of course, the common thing between them is they deal with larger problem, very computationally intensive, and before people couldn't approach them because there was no computers, as you know. So where we start? This part you really, most of you have covered in your calculus, maybe 181. And I am going through it not to tell you new thing. Think of it as sort of refresher. And we can also look at this as basis for what we can do for future module. So the whole thing started by Isaac Newton. And here he is. So what did Newton say? Newton said that a function fx has a local minimum at x star point if fx star is less than fx star plus h, where h is a small negative or positive disturbance around x star. So what you need to do is look at the neighborhood, see what is going on, and if your point is at x star is the lowest point, you are at a minimum. Similarly, if I have function fx and I could have a local maximum at x star, if x star is bigger than any neighboring point around it. So these two definitions are concerned with local minimum. So here we don't claim to have the best minimum, but we say I have a neighborhood I define between 2 points, and I say within this neighborhood, this is the best point I have, the local minimum. As mathematicians love to say, there is necessary and sufficient conditions. Let's start by necessary conditions. And you start with saying if we have a piecewise smooth function defined between intervals a and b, and before we continue, let's look at what piecewise smooth. The first case here in these three cases is piecewise smooth because there is no jump between any 2 points within this range, and the slope also continuous. If you go to the second graph, you will see piecewise but not smooth. Why it is piecewise? Because there's no jump. You continue, but you see there is kinks here and here, which means the slope is not continuous. If we go here, it is not piecewise and it is not smooth also because the slope is different at these 2 points. So if I go back to the definition, if I have piecewise smooth function, sine or cosine are great examples. There is extremum within this interval AB if df by dx, which is f prime as we will call it, is equal to 0. Okay, and you can see this very clearly here. Slope is 0. I can call this local maximum between this point and this point. Similarly, between 0 and this point, it is local minimum, etc., etc. If I go here, here is a local minimum, and here is a local minimum. But here df by dx is not 0. Actually, I have two values. One comes from the right, one comes from the left. Here, of course, I cannot apply this definition. And even if I have piecewise smooth function, you will see that you fail at function f equal x cubic, which I should have plotted, but I could do it now for you guys. It will look like this, not to scale. So you go to minus infinity on the negative, you go to positive infinity. Slope at 0 is 0, but it is not minimum or maximum. So let's go now to the sufficient condition. In sufficient condition, again, we are talking about piecewise smooth function between a and b. I will say that let me monitor the derivative at x star. So if it is 0, 0, 0, I keep going till I see the first non-zero derivative. And I will look at the value. If it is greater than 0, positive, and the n is even, I'm at minimum. If it is maximum and the derivative is less than 0, sorry, if the n is even and the derivative is less than 0, it is maximum. If n is odd, it is neither minimum or maximum. In this case, it is inflection or saddle point, like what we have seen with the x cubic. As you can see, my handwriting is not really good, so I will try to avoid writing as much as I can. Okay. How we prove this? We can go to the Taylor theorem, which again, I'm sure you have seen it somewhere in your life before. And Taylor, who he is here, again from British school, like Newton, but after him, he say, I can say that at a point away from reference point delta x, I will see fx plus dfx by dx delta x plus 1 over 2 factorial, second derivative by delta x squared, etc., etc., etc. And if you have huge number of infinity number of terms, you will have the exact value. So let's see how this applies here. So if df by dx is 0, of course it is not adding anything to this point. If I'm adding positive number, so this will be the second derivative, it is even. And let's assume that this is positive number. It means that this point is bigger than the reference point, x, and therefore I am at minimum. If this is negative, it means that this point was bigger because this will be taken, it will be smaller, so I am at a maximum. And you can expand it for various order, not just 2, but you can apply it, of course, at 4. So this is the end of this module, and we'll see how we can apply it in next one. Thank you very much.